Hello, everybody. I hope everyone's having a wonderful day. So today's Friday. I just wanted to mention a couple of things. So how many people have taken a look at the assignment or even started working on the assignment? I see some hands in there. Excellent. Okay, good. Excellent. Good, excellent. Yeah, I recommend getting started on the assignment. Depending on where things are at, it might take a little while, but I promise you, it'll be a good time. I'm enjoying the emotes of the thing. Excellent. But yeah, no. So I recommend getting started on the assignment as soon as you can. The sooner you start tackling it, the sooner you can get it done. But yeah, you can do the first few problems already at this stage. But anyways, with that being said, I want to get back to where I was last day. Actually, before anything, are there any questions about the assignment? Or is everybody doing fine? I just wanted to make sure. Are we all good? I think we're fine. But if you have any other questions or anything, just bug me after class or send me an email or bug me during office hours. I'm more than happy here to help out, okay? So, that being said, let's get back to where we were last day. So last day, I started introducing this idea of non-determinism. So I tried to give you a couple of motivations about what this non-determinism thing is. So with a machine in a deterministic setting, we had it where I start in one state, and then if I read an input symbol, I can transition from one state to another state, but it's deterministic in the sense that I go from exactly one state to another state, exactly one. In a non-deterministic machine, we're going to have it so that we can go from a state to possibly a set of states. And then we had a couple of weird, but kind of weird and magical ideas for how our machine could do things. So for example, we had this idea that the machine is capable of being able to process, like if I give you some string, it's able to correctly guess all the possible transitions to get me to an accept state on that given string. But as long as at least one exists, that's one set of transitions that gets me to the final state, it will accept. If there's no such path, it will reject. So there was this idea of perfect guessing. And then I also try to motivate it with this idea that you can imagine these machines kind of like as these massively parallel machines where you spawn these threads every time you do a transition. So there's a couple of these different useful ways of thinking about non-determinism. In different settings, you'll find these different concepts are pretty helpful. I'm hoping that I'll hopefully be able to motivate both of them in today's class. So just before I get into defining what the heck a non-deterministic finite automaton is, I want to just give you an idea, just a flavor for what we're going to be in for. Because it's very easy for me to talk about these weird hypothetical scenarios and not show you something that you can at least relate with. So imagine I have the following. This is going to be what we're going to call an NFA, or a non-deterministic finite automaton. So I'm just going to draw out this transition diagram. We're going to get quite used to seeing this one. So the first question I really have for you. So this is the transition diagram. The first thing that should stick out, can somebody point out something about this transition diagram? Actually, let me label the edges. Let me draw a couple edges here. There we go. Is there anything about this transition diagram that looks a little strange to you? That looks different from what we did with DFAs? Yeah, so that's the first thing you should notice, is that in a DFA, we define transitions from one state to another state on every symbol, right? So there was always a state that I could go to from one to the other on a symbol. In an NFA, we're going to find out that you can actually have it where you have no state to transition to. So for example, if I was at Q1, just hypothetically speaking, if I read a 1, there's no way this thing is going to possibly reach Q2, right? The question is what happens? And what happens is going to be essentially motivated by the same idea we talked about with the parallel threads, where you can imagine the execution like a bunch of parallel threads all going at the same time. If I don't have a transition, that thread of execution, it ends, it dies, it gets killed. So if, for example, I read a 1 when I was in this state, there's no way I could possibly reach Q2, and at that stage, you'll just say, oh, just reject. But you're going to see it's a little bit more complicated than just that with the NFAs. Another thing I want to hopefully point out is that notice that this Q0 has a self loop here with a 0 and a 1, but it also has an arc going from Q0 to Q1 on a 1. So notice that it's actually able to have the ability to transition to 2 states at the same time. Isn't that wild? So isn't that kind of, that's a bit weird, at least compared to the DFA. So in today's lecture, I'm going to be giving you some background for how you can interpret this with so-called a non-deterministic finite automaton. We're going to design some and see how far along we get. We might get to some interesting stuff later. All this stuff is interesting, but I really just want to motivate this. So we can see a couple of differences already at this stage, but we see it's generally like, it looks like something we can kind of relate to. That's the big gist I want to get us to. So I'm going to define something called a non-deterministic finite automaton. So this is an NFA. So my hope is by the time I'm done talking about NFAs, you're not going to feel like these are so much magic. That's my hope. Is that before I talk about non-determinism as this like magical idea, my hope is to dispel this idea with specifically this construction of a machine. Because there's another way you could think about it. So again, you're going to see that this definition is going to be almost the same as the DFA. But I'm going to write it out because I want you to know it. It's a quintuple, or 5-tuple. A Q sigma delta Q0 F. This is exactly like the DFA with the 5 fields there. Where? So Q is a finite set of states. Can somebody tell me what's sigma here? Is that the set? What is this called? The set of starts with an I? Somebody tell me. Well, so this would be the alphabet for the language you want to recognize, but we call this the set of input symbols for the machine. But it definitely, you're thinking the right thing. Excellent. So sigma is a finite non-empty set of input symbols. So just like, keep in mind, this is all so far exactly the same as you would anticipate. Just for dramatic purposes, I'll just keep going, where I'm just going to skip over delta, because delta seems to be the thing that is a little bit odd here. So Q0, again, is the start state. Is the start state. And we have F, which is just a subset of all the states, is the set of final or accepting states. So that leaves delta. Now delta is going to be a little bit different, but it's not that much different. I'm just going to make a small tweak to it. So delta is a transition function. Is a transition function that takes as inputs as inputs or arguments, however you want to say it, a state, and a symbol, then returns a subset of Q. Like I said, instead of going from state to another state, it's going to go from a state to a set of states. Some subset of Q. In formal terms, or more formally, delta is a function that takes a set of states and an input symbol, and it gives you some element of the power set. So this is the power set. Some people also write this like 2 to the Q like this. To the power set of Q. So this is the power set. So like I said, it's going to give you back a subset of Q. All possible subsets of Q is the power set of Q. So that's what delta is. Any questions about this definition so far? The only thing that seems a little different is that thing. Is everybody clear on what power set means? I just want to make sure. Because I could give you an example if it's been a while since you've heard what a power set is. Sure. No worries. No. So imagine I give you a simple set like this. Say actually I won't call it A because I just defined what I defined an A. I'll call it B, and say I have A and B like so. The power set of B would be the empty set. It would also consist of the set A, the set B, and the set AB. So it's all possible ways you could grab one of these elements from B. So the power set of B would consist of the empty set. I pick this one, I pick that one, then I take both. So it's just all possible ways you can have a subset of B. Does that help? Perfect. Yeah, that's exactly what it is. So that's what I mean by it returns a set of states. So when we talk about Q, I'm talking about every single subset of Q. So that includes the empty set, which is, you might ask, Dan, what does this mean where I don't have a 1 or anything here? That's the empty set popping up right now in our transition diagram. Perfect. So let me, let's do an example, because I already have a picture here. So it's okay by any odd chance if I remove, I was about to say delete. It's been Fridays. It's Good Fridays, I guess. It's okay if I remove this so I can write down an example? I'll go through each one of these with the example. Perfect. Because I'm going to do an example with this transition diagram in question. And I'm going to try to give you some intuition about how all this works, and then I'll give you a formal definition just like I did last time, where I'll give you an extended transition function. That's where we're going to be going with this. And then we'll design some NFAs. And depending how far along we get from there, I might get to show you some really neat thing. Okay, so let's do an example. So consider NFA M equals Q sigma delta Q0 and F, where we're going to say Q is Q0, Q1, and Q2. So I'm going to have these 3 states here. I'm going to have input symbols. These input symbols are going to be binary, so just 0s and 1s. And let's since it's in this order, I will do I'm going to do a transition table, seeing as I have the transition diagram. because it's important I show you how to do it both ways here. So I have 0 and 1. Now I have Q0, Q1, and Q2, just like what we do normally with our transition table. I indicate the start state, that's Q0. I indicate the states that are final or accepting states, just like I did before. Like I said, all these rules are generally going to fit across the board for most of the things we're going to talk about in this class. So I don't even have to explain this in more careful detail with you. But the thing that's going to be different now is the entries in this table. Because remember, I told you the delta is going to spit out a subset of Q. So instead of it just being a single state like before, it's going to be actually a set that's going to be right here. So get prepared to write a lot of curly braces. So just giving you some warning. Okay, so if I'm in Q0, if I read a 0, you'll notice it says, okay, 0, it goes back to Q0, right? So the set I would return consists of just Q0. So notice it's just a set. It just has Q0 in it. That's the subset in question. Now I have a question for you. If I read a 1, what should go inside this set? So, perfect. Q0 and Q1. Everybody's getting this. I see it in the chat too. Awesome. Q0, Q1. And how about Q1 read a 0? What should I put here? A set containing what? Q2. Perfect. Perfect. You guys have got this. Awesome. I'm loving this. And how about here? I alluded to this earlier. It's empty. Yeah, it's empty. There is no, remember, the empty set is a subset of Q. So just be careful when you see this. You're like, okay, well, why would the heck would that be there? It's because remember, that's just a subset of Q. Just like technically a subset could be every single possible state. Which is kind of wild. So how about right here? If I read a 0 with Q2? Empty. Yeah, empty. Perfect. And right here, somebody tell it for me. Where I read that 1, it's Q2. Perfect. See, there's our transition table. Bing, bang. You're all pros at this. Awesome. So there's our transition table. So I'm just going to, so I'll say delta as described by the transition table. I'm just going to draw an arrow here. It doesn't matter. You could just say it below or wherever. I'm just doing it because we're having a little bit of fun here. If you're writing this more formally, you would say delta as described by the below transition table or below transition diagram, whatever it might be. And of course, Q0 is a start state. And what's F? Somebody tell me what's F. So what's going to be F? The set of final states or accepting states. Just Q2. Yeah, just Q2 is just going in here. Like I said, the only thing that differs at this point is this transition function. That's the only thing that's changed at this point. Is everybody all good right now? Just don't be shy. If you have any questions, please stop me, okay? Because I assure you things are going to start feeling a little weird when we start doing this, but I'm hoping that the things I said at the end of last class will help inspire what we're going to do next. Okay, so now I have this, and now what I want to do, I just want to give you some intuition behind this before I give you the extended transition function that defines the computation of the NFA. So I'm just going to put this table here. I'll draw it right here. So imagine I give you a string W, and say it's 01101. Now, what I'm going to do is I'm going to show you how the NFA may process this using the inspiration of the parallel thread idea. But I'll also show you how the perfect guessing sort of pops into this too. So I'll draw it up here. So when I start off in the starting state Q0. What happens next is, just like a DFA, I read the 0. I read a 0. If I read a 0, it tells me you're currently in state Q0, right? That's the only state that's in this set. Okay, when I read a 1, this is where things start getting a little bit funky fun stuff. Okay, so it could be in Q0 or in Q1, as we have in our transition table. So it could be Q0, and it could be Q1. So these are currently the set of states that I am currently in with my machine. So if you're looking at this more like the parallel inspiration, you got to think about this like when I make this fork like this. Now this is another independent execution of my machine, if you want to use that way of thinking about it. Another way is you're going to see that eventually I'm going to reach some path, or that it's going to accept, or all possible paths are going to reject. It's very asymmetric that way. So it's essentially I get like acceptance essentially by taking any one of the paths, but if no such path exists, then I reject. So now if I read in another 1, now notice here that on Q1 there is not any transition, right? Well, it tells me the transition to no states, right? So this is going to end right here. So this thread is going to die. It's done. It's done. So I'm going to read a 1. So notice this will transition to nothing, so it just dies. And I mean dies figuratively, of course. Like dies, I mean more in a technical sense, not like literally like I'm going out with an axe and coming after the machine. That's not happening, okay? So anyway, so now Q0, when I read that 1, the same thing happens again. I transition from Q0 to Q0 or to Q1. And then what happens is I read a 0. If I read a 0, if I'm in Q1 and I read a 0, where should I go? If I read a 0 from Q1, Q2. So this thread will go to Q2. This one, however, because it's reading just a 0, it stays in Q0. Then what happens is I'm sort of running out of space, but I think I just have just enough. Okay. So then I read the 1, and I promise it's a little squished in here. I'm going to, when I read the 1, Q0 again, it goes to Q0 and Q1, just like before. And then when I have Q2 and I read a 1, because there's a loop on Q2, I stay in Q2. So I'm still in Q2. But remember, I've finished reading the entire string. But what does that mean? That means that like, okay, so how do I know it accepts? So I'll tell you first that it will accept right here because Q2 is a final state, right? So there's two ways you can look at this. You can look at this like the entire execution if I were to exhaustively do this. That's one way you can look at this. And you'll notice that there exists a path of execution that gets me to Q2. So I accept. If I were to reject, that would mean all possible forms of execution of this, given that string, would reject, or the thread would die. In the perfect guessing world, like if I think about this as like the machine's capable of a perfect guess every time, so it has this ability, this clairvoyance to be able to take the path that leads me to an accept state if it exists, what will happen is it goes Q0, 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 Q1, Q2, Q2. And it would say, yeah, no, it accepts. It accepts. It exists, so it accepts. So does this help a little bit with seeing how these states get formed? So I'm just showing you that by transitioning, now I can have it where the states can basically fork off each other, and now they could be in multiple states at the same time. Are we all good with this? So this is just to give you a visualization of this process. I'll give you an exact way of looking at this, and you're going to see, oh, look, really, this picture is actually just saying the exact same thing I'm going to say in a wee bit. But are we all good with this? Because I just want you to keep this in the back of your mind as we do the extended transition function. Then I'm going to do an example, and I'm going to connect this picture up with some examples. That's essentially the game plan for the next little while. And I made sure to include in the notes some extra examples so you can see how this extended transition function works with a couple more strings. Because I feel like for some students, when they don't get this idea, like sometimes just really have to just drill it out and just try it out by hand. And I think that sometimes can be a little helpful. So I'm going to give you now a formal definition of computing. That C sort of melted into the O, like some ice cream or something. Computing for a DFA. So I'm going to again define the extended transition function. Now, so remember, an NFA takes a state and an input symbol, and then it returns a set of states. So similar to a DFA, so similar to a DFA, the extended transition function, takes, we're going to call this delta hat again. Just want to make sure. Can everybody see this delta hat right here? Just want to make sure. Sometimes I lose ground on what I'm looking at. Okay, I think we can see the delta hat. This delta hat right here. Okay, good. Okay, so the extended transition function delta hat takes as input a state and a string of input symbols, That's what we'll say input. State of input symbols, but, need a comma, but, this is the big but. Okay, so, but instead returns a set of states. So, which what you would expect, because the NFA, when you transition, returns a set of states. So we're going to define delta hat as follows. So I'm going to define this inductively like I did before. So I'm going to have a basis and an induction part of my definition. This, I will give you a heads up. This definition is a little bit easier to understand inductively than it is recursively. That's at least my thoughts about it. You'll see when we do the examples that it's going to be feel more like a process that you can't really, it'll feel a lot more like, a student pointed this out last time, that it'll feel more exhaustive. So this inductive way of looking at things might be a little bit more helpful. But like I said, there's another way of looking at a lot of these things. So delta hat of Q epsilon, so just like before, I'm going to define it for the empty string. It's going to return me a set containing Q. So imagine your favorite child, you put them in their favorite little outfit. That's basically all I'm doing. So that's my favorite child, I put it in an outfit. I just put curly braces around it. When no symbols are read, the NFA stays in state Q. So that's the first part. Now the second part, this is, I'm giving you a heads up. This one's gonna feel a little bit strange if you haven't seen union applied in this way. So let me just be careful when I explain this for you. So we're going to have the same idea where I'm going to have the string, I'm going to pull off the last symbol, and then I'm going to have everything else. That I'm going to do the exact same thing I did last time, except it's just the way it processes it. Given string W equals XA, where A is the last symbol of W. And you can clearly see that I don't like using the word clearly, but X is everything but A. I'm just gonna keep it at that. So we compute. So this is just, first I'm gonna give you an informal intuition with this, and then I'm going to define it formally for you, because I think the English description of it first will help with this before I write it down mathematically. So compute delta hat of qx. So remember, that's on this first part. Delta hat qx, then follow any transition labeled A. From this, it says this set of states. So you're going to imagine I have this. I have delta hat qx, and then I'm just going to have some set of states that are the result of that. What I'm going to do is I look at symbol A and I look at all of the states that the set of states that I have here can all transition to at the same time. So once I write it down formally, you'll see it. Okay, formally, if delta hat of qx is equal to the following set, I'm going to call it P1, P2, all at the pk, like this. So these are all going to be the set of states that it will be after it finishes processing x. Then this is how I'm going to define it for w. Delta hat of qw is going to be equal to the union from 1 up to k of delta of pia. So if you're wondering what that big union does, it's kind of like this sigma or product. Like when you see a summation, you have it like you sum the terms. This big cup or big union is just simply going to take the union of each one of them indexed from 1 up to k. So what I'm saying is you take the union of P of the transitions you get as a result of P1, comma A, P2, comma A, P3, comma A, and so on and so on and so on. Is that clear, everybody? So you're just going to take all of them and lump them together. We'll see it when we do some examples here. You'll see that this looks a little bit more involved than the one we've seen before, but ultimately it's really built around this idea that we have a set of states as opposed to just a single state. Are we okay with this definition? I just want to make sure we're all good. Are we all good? Okay, I see some. Okay, does anybody have any questions about this? I just want to make sure. I assure you we're going to see a couple of examples how we could process using that machine I have over there. I'm going to do some examples using this. So if at first this doesn't seem very intuitive at all, don't worry. I'm going to do some examples with this. Okay, so I'm just going to proceed. I'm just going to keep the transition diagram up here. I don't need the table per se. I'm going to keep that there. I'm going to need that. Okay. Okay, so let's do some examples. So I want to do an example here with you. So suppose W is equal to 0, 1, 1, 0, 1. This is the exact same string I did over here. I'm doing this for a reason, so that you could see the connection between that picture and what I'm going to do over here. So I'm going to do just like I did before. I'm going to start off with the empty string, and I'm going to build up the string one symbol at a time. So I'm going to start off with delta hat Q0 epsilon. And we know that this is just simply that set, put curly braces around it. That's the basis or base step. Next, I read the first symbol, which would be a 0. So I have Q0, 0. Remember, I'm going to build up to my W here on the left side. Now, remember, now this is where it's going to get a little bit interesting. Okay, so I already have a set of states here. This is my P's over there in that definition. So when I had P1, P2, P3, all the way up to PK, that's this right here. That's what this is. So all I'm going to do now is I'm going to apply the transition function on any one state that's in here. In this case, I apply it to Q0. And I do it on the symbol. That's the last one that appears here. So this is just simply going to be Q0, 0, which it just takes me back to Q0. Okay, are we all good with this so far? Okay, let's proceed. Delta hat Q0 of 0, 1. So now I'm going to consider 1 here. So now I just take the union of all the transitions I can take on this set, but that's just Q0, right? But I'm going to do it on symbol 1. Remember, that's what A was over, yeah, A was over there. So I have Q0, 1, just like this. But where do I go now? Now it just goes to 0 and 1, Q0, Q1. Now this is where things start getting a little bit more interesting. Is everybody following me? I just want to make sure. So all you got to look at is I take this and I apply the transition function to each state that's in here, given the symbol in question. So in the next step, what's going to happen here? When I read that next symbol, I'm going to take the transition function on the next symbol is a 1. I'm going to take the transition on Q0, and I'm going to take the transition on Q1. And I'm going to lump those two together using union. So delta hat Q0, 0, 1, 1. This is going to be delta of Q0, 1, union delta Q1, 1. But we already know what this is, right? That's just this. But what's this? Somebody tell me while I'm writing down Q0, Q1. What's the transition on state Q1 given 1? Empty. Yeah, it's the empty set. Perfect. So the union between Q0, Q1 and the empty set is just Q0, Q1. Q1. Okay, now I read the next symbol. Got 0, 1, 1, 0. The next one's 0. So now I'm going to just do the same thing. I'm going to take each one of the states that's in that set way over on the right there. And I'm going to take the transition on each given 0. And I'm going to take the union over all of them. So Q0, 0, union, delta, Q1, 0. But what's this? What's this? This, so if I give you 0 on Q0, it just takes me back to Q0, right? If I'm in Q1 and I read a 0, where do I go? Somebody yell it for me, okay? Where does it go? It goes to Q2, perfect. Perfect, you guys are right on the ball. Perfect, I like that. Q0, Q2. So if I just take these together, you'll see that That's Q0, Q2. Now remember, it's union, so just keep that in mind. So if you ever worry, oh, I have a duplicate in there, don't worry. Remember, union, it's a set. So if there's multiplicities, they just sort of, we only care about them being unique. So delta hat, now we have the last symbol here, Q0, 0, 1, 1, 0, 1. So this is W. So I'm going to take each one of those, and I'm just going to apply the transition on symbol 1, Q0 on 1, union delta of Q2 given 1. This with a 1 takes me to Q0 and Q1, right? Q0, Q1. Q2 given a 1 just gives me Q2, right? So notice that this contains all the states, Q0, Q1, and Q2. And you might ask, Dan, how do I know that this, because previously we established that this string, it will accept for that machine. How do I know that it accepts? Does anybody have any ideas of why this string accepts given this? Yeah, Q2 is right there, right? So notice that, well, Q2 is in F, right? So we accept. Perfect. So that's going to be really the big thing that we can use to test whether the string accepts or not, is if one of the states that we're left with in our set of active states is the final state, or is a final state. We need at least one of them there. Now, I want to blow your mind for one moment. I'm going to, so I want you to look at these rows here. I have Q0, Q0, Q1, Q1, Q0, Q2, and Q0, Q1, Q2. I want to just blow your mind here, okay? So I'm just going to take a different marker. Actually, now for dramatic purposes, I'll do the following. Here we go. So if I read Q0 right here, notice Q0 is right there. Q0 is right here. Q0 is right there. Q0, Q1 is right here. Read the column, Q0, Q1. Look, Q0, Q1 is right here. There's Q0 and Q1. If you read the columns, they match up with the rows of my calculations. So just, you could keep going. So for example, if I have Q0, Q2 here, look, it's Q0, Q2 right there. And long and behold, if you look at our final calculation here, if you think about like threads, there's a thread active with Q0, there's a thread active with Q1, and there's a thread active with Q2. Boom. Is that neat? So if you ever find yourself really having a hard time with this extended transition function, try drawing a picture like this and see if it matches up with your calculations here. So you just read the columns. So if you just look at it like, if you read the columns of these, if you read these, they match with the rows of my calculations. Is that neat? So I want to do one more quickly, and then we're going to do a couple of designs. So I threw another example in here so that you could try it out yourself. But I will do one quicker one here. So imagine, so let W be 1, 1, 1. Now, the first thing you should ask yourself is, Dan, does this string accept or reject? I'll let you think about that while you're looking at that. So I would do the same calculation I did right here with the empty string. Delta hat Q0 epsilon just gives me Q0 like before. I read a 1, so Q0, 1. Now, notice that this is just me computing the delta of Q0 given 1. What's that? That's just Q0, Q1, right? And if I read another 1, if I have Q0, 1, 1, I read the second one here. Notice I have Q0, Q1, so I would take delta of Q0, 1, union delta Q1, 1, 1. We've established, we actually calculated this earlier, but you'll notice that this is just Q0, is this Q0, Q1, right? That is the empty set, right? So you know this is going to be Q0, Q1 again. So I want to ask you, if I do one more, I do one more symbol, is this going to accept or reject? It's going to reject because it's just going to give me Q0, Q1 again. So why? Because I've gated off Q2 by putting a 0 right here on the transition. But I really want you to observe that as I'm doing this, that really what's sort of happening is, I want to come back to this idea of the guessing, is that by having a loop here, I basically allow myself a free guess every time I go back around this loop. Say if the string eventually can allow me to get back over past here to get the Q2. Do you see that? It's sort of like, hey, look, if I read a 1 right here, I want you to think of it like a DFA again, but ignore this 1 right here. And imagine I read a 1 here. If I read another 1, it would just say, no, there's no 1 here, right? Like technically in a DFA, we'd probably have a loop here, but we're just trying to keep this simple here. You'd know that this would just, the thread gets killed here, right? But in contrast, because this self loop exists, it always allows me to create another thread of execution that allows me to stay alive. Does everybody see that? So no matter how many 1s I put into this thing, it's never going to technically, it doesn't get killed, right? It's just going to keep giving back Q0, Q1. So if you were to try delta hat of Q0, 1, 1, 1, you would end up with just another time you'll get Q0, Q1 again. And none of these, so none of those are an F, so you would reject, right? Does everybody see that? I know this is a lot of calculations on the board, but I want to bring this all together now. So in the notes, I gave another explanation for this producing of more guesses. I created a modified DFA that is essentially this one without the self loop on the 1. I'll encourage you to take a look at that in the notes. It's the same idea I just explained here. Just if you want to see another example, it's just another example. Okay, so let's talk about the language of an NFA. So you might ask, okay, well, how do I know, like, what language, if I give you an NFA, what is the language of that NFA? I gave you a formal definition the other day for DFAs. So given an NFA M, if I say L of M, I want you to take what we just described over there, and I want you to apply it to try to help me define the language of an NFA. So I have a string W. You know it's going to involve the extended transition function in some way, Q0 and W. But what do I need to know about that? Remember, this is a set of states here. Feel free to use any set theory you could think of to tell me what. Yeah, so it's going to involve F, and you're going to take what thing? Let me say it again for me. Yeah, it's going to be some subset of F. I'm going to write it this way. That's perfectly fine. Like, you'll see why I do this a little bit later on when I talked about some other interesting idea. But yeah, that's another way you could say it. It's a subset of F. I'm going to say that this intersected with F isn't empty. That's another way you could say that. But that's a good suggestion too. I like that one. But the only reason why I want to make sure that that I have it, like the reason why I was thinking about that one a little bit here, is that if you were to define it as just a subset of F, you need to make sure at least one of them is the final state, right? A subset could contain the empty set. So you just have to add one more thing to that. You'd have to say, oh, that this is at least one, right? But other than that, it's a pretty good suggestion. But yeah, no, so that's the language of an NFA. Now, can you give me 1 or 2 more minutes? I want to do one example with you so that next time we could come back and do a couple more examples. I promise it will not be very long. I want to do one example with you. Let's do an example. You're going to see that this idea that I could just produce more guesses is going to be really helpful for us. So I'm going to do one quick one here. So we're going to design NFA that accepts all binary strings where the third last position, let's go third last position. I was going to say first, but let's go last position of the string is a 0. So just as an example, just to illustrate this, so 1 1 0 1 1 1 and 1 0 1 0 0 0, these all should accept. Actually, sorry, let me make sure here. I think we need the 0 right here, right? Third last position, yeah. And if we want to reject, could somebody give me a string that would reject under this idea? So 0 0 1 0 0. Yeah, that works. Perfect. So that rejects. Like 0 0 should also reject. These are just some examples of things that this should certainly reject. Now, I want to take the idea I had over here, where if you actually take a look at my NFA on this side, I gated off the strings from reaching the final state by imposing a 0. I'm going to try to take that idea and extend it. So I'm going to create a chain. It's going to remind you a little bit of when we did the substring example, because it's essentially going to be the same kind of trick we're going to use. So I know for certain if I want the third last position to be a 0, if I make a chain like this, where I make sure that's a 0, and I allow this to be 0 or 1, and that to be 0 or 1, I can ensure that I can reach some final state Q3. That's the first thing I would think of trying to do, is try to make it so I impose the 0, and then I allow anything else, but nothing more, because it has to be the third last position. So let me label some states here. I got Q0, Q1, and Q2. Does anybody have any ideas of what else is needed here? There's something missing. Does anybody see what I need to do with this? I'm missing something, because if I just read it like this, I have 0, and then I could, but you'll notice that, there's nothing really to keep me getting more guesses. So what do I do here? So I heard about a loop. Loop's a very good idea. Let's put a loop right here. So let's put a loop right there. I think this will cut it. Because remember, when you think back to the idea we had over there, if I keep reading in binary strings, like with 0s and 1s like this, if I read a subsequence of them, I can read a bunch of 0s and 1s, but as soon as I counter a 0, one possibility is it's going to stay in Q0, and it's also going to have another possibility where it's going to go to Q1. So if, for example, hypothetically speaking, somehow it was able to read more than 3 symbols when it reads a 0, then something, then a something, there's no transition here, so that thread would get killed or ends. But this loop allows me to keep around longer strings. Does everybody see that? So I could just keep, I don't like to use the word generate, but it essentially will allow me to have some thread of execution staying right here in Q0, so that when I eventually read a 0, then 2 other symbols, it will get me to Q3 over there. But if I read any more, that thread will just say, bye-bye. Is that clear, everybody? So this is just an example of one such NFA. So when we come back, because I need to really let you guys go, we'll do more examples with NFAs. Then I'm going to be transitioning to I would consider one of the first really powerful ideas in this course. So that'll be where I talk about subset construction and some other neat things. So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.